All right, question 3 says the circle at the right represents a planet. It says the radius of the planet is about 5,100 kilometers. Find the distance D to the horizon that a person can see on a clear day from the following height H above the planet. Okay, so zoom on this picture a little bit. The scenario, I think it's important to maybe understand what they're talking about here. So you're on this planet, okay? So kind of view like maybe you're on let's view this as the equator, okay? And there is a structure that is H units long. In this case, it's 7 kilometers tall, okay? And you're on top of that, okay? And if you look out, you should in either direction. Okay, you should be able to see kind of the curvature of the Earth, and your line of sight, okay, should be tangent to that point on that circumference. Does that make sense? So have you ever been to like the top of a lighthouse or maybe a tall building or something like that, and you look out and you ever wonder how far can I physically see? This is what's going on. Okay? The answer to that question is D here. Okay. So when they ask us to find that, basically what's going on here, and this once we put all the values in the right spots, it turns out to be a very similar question to what we saw yesterday in the notes. They tell us that the radius of the planet is 5,100. So this distance right there is 5,100. Okay? That distance there is also 5,100. This is 7. So what we've got right now, I'm going to use this distance right here as this. So that'd be 5,100. Okay. This distance here of R plus H, I'm going to say is 5,107. And then this distance D, so come down and make this right angle right here, would be there. Does that kind of make sense? So what can I use then to find D? I can use the Pythagorean theorem. So I'll write this out. 5,100 squared plus D squared equals 5,107 squared. Go ahead and finish. I'll let you finish solving that, but that's how you would finish that problem. Okay, so that's question 3. Does that help? Question 4, same idea. Now, in question 4, the algebra in question 4 is a little bit more intense here, because when we look at the triangle that's being produced, if that's the right angle where this is 15, this is x. Now my hypotenuse, which would be O to that point right there, how long is that hypotenuse? 8 plus x. So then if I take the legs, 15 squared plus x squared should equal x plus 8 squared. So we get 225 plus x squared. Now this is where we make mistakes, because we want to write that as x squared plus 64, because we square the first thing, square the second thing. But if we remember x plus 8 really means this, you need to FOIL, you should get then a 16x in the middle, right? The x squared is going to cancel. If I subtract 64 from both sides, it's 225 minus, is that 1? Okay, get there. So 225 minus 64, 161 equals 16x. Divide that by 16. Round it to the nearest tenth. That's about 10.1. This is our x value. But okay. Sometimes, and I don't know if any of the questions in your homework did this, but sometimes these x squareds might not cancel, just depending on what these were. Okay, maybe they gave me, this distance be maybe like 2x. Okay, so then maybe what I want to say is that it depending on how this. I don't want to hypothesize something that might not be true. But if for whatever reason you write this formula out here or this equation out, and those do not cancel directly, and maybe you're left with x squared in your equation, then you would have to factor, right? So you might not always get down to these x squareds just 100% canceling out and you can ignore them. You have to still always abide by what the math tells you. So if you get x squareds cancel out, great. It now tells me I have a linear equation to solve. If they don't cancel out, then I got a quadratic equation to solve, and then I have to go down that route of factoring using quadratic formula or whatever may be the case. Did you say 6 was another one? 6. Okay, so this is just an extension of the theorem that says if I have a circle, and from that circle there's a point on the exterior of the circle, there should be 2 tangents that can be drawn to that circle. There's one, and there's the other, right? Okay, kind of a crude drawing, but let's say that those are tangents. What did we talk about yesterday? The length of how do those lengths relate to each other of those tangents? They're congruent. Okay, so those 2 distances are the same. So over here, based on the word circumscribes, okay, the polygon circumscribes, so that means it's been drawn around, but there's the math connotation is that there are points of tangency. These lines are tangent, or these segments are tangent at those points. Okay, so if I look at, we'll just do this one right here. That right there, and that right there, that, if I remove the other segments there, this picture looks just like this picture, right? So if this is 13, what is this distance here? 13, okay? Now, as I move around, if this one is 8, what's that one? 8. If this one's 4, and then this one's got to be 6. So now we've filled in all the unknown values. If I want the perimeter, then I'm just going to go through and add those up. Double it. Like a double. That's not a bad approach. Just make sure that you know that first Wednesday of the month. So if this was like, because I've seen questions like this where they maybe give you both those right away. So I wouldn't want to add everything up and double now because that 13 would be doubled one too many times. But yes, you could take one of the congruent tangents, one of these congruent tangents, one of these congruent tangents, one of those congruent tangents, add those together, and because of the congruency idea, double it, and you should get that total. That's a good recognition there. Did you say 8? No, 11. In the figure to the right, lines that appear to be tangent are tangent, and O is the center of the circle. What is the value of X? If this is a tangent right here, and this is a radius, so a radius and a tangent, how do they intersect? If they intersect at the point of tangency, they intersect at a right angle. So then the same thing happens up here, right? Okay. So now what we're really looking at here is we have a problem. The reason they gave me the circle and the tangent lines and all that kind of stuff is so that I could get that image right there. Now I have that polygon. In the past, in chapter 6, maybe they started us off with this polygon and they had to start us off with these right angles. Now, because we know something about circles, they start you with a circle and delete those angles and see if you know that the relationship between the circle with its radius and the tangent lines will tell you that these are right angles. But in chapter 6, how many degrees did we learn that a quadrilateral had in it? 360. So to find x, I could take 360 minus one of the right angles, minus the other right angle, minus the 119 that is there. When I do that calculation, that will leave the one unknown angle x, x left over. We're cool with that? All right. I want to talk. Go ahead, sorry. Nope. Says PQ and PR are tangents. 2E. So we haven't talked about this, but that's the way. Hopefully, we realize that that's the way that we say circle E, right? So I'm writing the word circle out, kind of like when we do triangles. But they put a dot in it, so it doesn't look like an O. Okay, so if you ever see that notation, that's what they're talking about. Find the value of x. So what do we know? So this is these are tangents. Okay, and if they are tangents that emanate from the same external point and they go to the same circle, what do you know about PR compared to PQ? They're equal. Okay, segments are congruent, distances are equal. So we're going to take 7x minus 32 and set it equal to 3x plus 4. We cool with that? Any others? We're good? If you got questions on it tomorrow, let me know. We can talk about that again. I'd like to get into talking about, they're called inscribed angles. There's a lot of different angles that we can discuss and talk about when we talk about circles, which might be kind of odd that we talk about angles when we're talking about circles, but the most prevalent type of those angles is what we call an inscribed angle. Okay, so it's the same word that we've seen before. We've seen inscribed polygons. If you remember back to, you guys remember talking about orthocenters and incenters and all that kind of stuff? Those fun triangle stuff. The incenter, what that did for us is it created an inscribed circle. So the circle was inside something. When we talk about inscribed angles here, the angle is actually going to be on the inside of the circle. Okay, the angle is, so inscribed is an adjective to describe what type of angle we have. Okay, so an inscribed angle is an angle whose vertex is on a circle and whose sides contain chords of the circle. Okay, so this is the side of my angle. Okay, and that is then a chord. If you remember talking about chords a couple days ago, that is a chord for the circle. This is another chord, which is also another side of my angle, and my vertex is on the circumference of the circle. Okay, so this angle right here is referred to as an inscribed angle. Okay, the picture on the right, the circle on the right, is also another inscribed angle, and we can have all sorts of different inscribed angles. I'll show you a couple more here. All right, so here, just color these segments. Okay, those segments there are chords, and no matter how I move this around, that is an inscribed angle. Okay, that green angle is inscribed. I can move it over here. Now it kind of, because of my location of C and D, let's move C and D. I think this will work. And now move that over there. There we go. So we can see it over here, still an inscribed angle. Is that all right with everybody? And the size of that inscribed angle changes as I move point C and point D. Okay? Now, do you guys remember, so the way that GeoGebra is programmed here, I can ask it to find an arc distance. So let's see if we can do that. I can go there, from there to there, and that shows me, so that blue arc, okay? If I ask, and you see right here, it gives me the number of 2.9125. That is the distance from C to D. Is everybody okay with that? Okay. Do you guys remember, let's see here, just lost my pen. That this distance can be found using the formula. Okay, so arc length is equal to x over 360 times 2 pi r, correct? Okay. What I want to do here is I want to get, and right now we're getting this blue distance to be reported by GeoGebra, okay? I actually want to take that 2.9125 number and I want to convert it into a degree. Okay, so if they give me the arc length, I should be able to determine from that the degree of that measurement. Okay, so if you remember, we'll walk through this kind of slow here. Basically what I want to do is I want to go through this and I want to solve for x in this problem, this expression. Okay, so I'm just going to call arc length. A lot of times what they call arc length, when you see formulas, they call it S for whatever reason, okay? So I'm going to say S is equal to X over 360 times 2 pi r. If I multiplied both sides by 360, would that make this X times 2 pi times r? Okay? And remember, I'm trying to solve for X here. All these other things are attached to X through multiplication, right? So if I divide everything over here by 2 pi r, those all cancel, leaving me just x. So then I take 360 times s divided by 2 pi r. And that will give me what this arc measurement is in degrees. Is that okay with everybody? So I'm going to type that. I'm going to see if GeoGebra can help me type that in here and actually turn this blue distance into a degree measurement. Okay. Now I'm not sure the way that GeoGebra is going to do this. I don't know what unit GeoGebra is programmed in right now. I don't know if it's in radians or degrees. So I'm going to type it in the way I think it is programmed, but I might have to adjust here in a moment with this 360, and I might have to change that to 2 pi in a moment. But we'll see. So that's I know I need the radius, so I'm going to ask GeoGebra to find the radius. I'm just going to color that purple so I know which letter here to use. So I'm going to go 360 times S. Well, S was this length. That was the arc length. We have that number right here as 2.9125, right? And it's being identified as D. So I'm going to take D, put that in parentheses, and we'll divide that then by 2 times pi times r, but r is this purple distance h. So I'll say h. Okay, so it's just a little bit of a redefining of variables based on what GeoGebra is calling r and is calling s and that kind of thing. So I hit enter. Okay, and it did what I was hoping it would do. Okay, so GeoGebra was programmed in degrees. So what we're saying here now is that this blue arc right here is 125.4707 degrees. Are we okay with that? I'm going to take, real quick, just this number here, which is alpha, and we'll divide it by that number there of 125 and see if there's a relationship. So take alpha, and we'll divide it by number A, and what it does, it gives me 0.5 as a result. Okay? So this number here is what compared to that number there? 2 times bigger. Okay? Now, because I've got this programmed, hopefully correctly, to show that it does not matter the size of the arc. Oops. I wanted to hide that, not delete it. Look at that number right there. As I move the arc, the size of the arc, the measurement of it and the length of it, those are those two values. The measure of it changes as I move C and D, right? Okay. This inscribed angle changes, correct? But does the quotient of the inscribed angle compared to the arc, does that ever change from 0.5? That make sense? So this arc measurement in degrees is always twice as big as our inscribed angle. And it does not matter how big the circle is and or how big the arc is. Okay? Always at that 1-to-2 ratio. So that is what this next statement is going to get at. Okay? It says the measure of an inscribed angle is half the measure of its intercepted arc. Okay? What's it mean to intercept something? Huh? To get, so you're thinking like intercept a football or something like that, right? Okay. What does that word really mean? Let's think about this. If you are a football player, and the quarterback throws the ball, right? Throws the ball at somebody, correct? An interception is when somebody else comes through and takes that ball right there, right? But this person that comes through and intercepts it, they cut through the path of the ball, right? So the word intercept means they cut through the path, okay? If somebody was passing a note through class and I intercepted that note, I would have cut through the path of that note going from person A to person B, right? Does that make sense? Okay. So when you intercept something, you're cutting through the path. So that's what's going on here. When we call the intercepted arc, it is the arc that is created as this ray cuts through a path and that ray cuts through a path. So the intercepted arc is the arc that is created by the inscribed angle. Does that make sense? Okay. Sometimes they refer to it as the subtended. I don't like to use that word because it's a word that we never use in any other aspect of life, but subtended, they'll refer to as the subtended arc or the subtended angle. It's the same relationship as an intercepted arc and an inscribed angle. Okay, but what we see is that the angle is always half of the arc. Okay, so what we've got going on here, think about this. Didn't we say back in I think it was section 10.6 or 10.7, that if I look at this angle, so we'll look at those being that color. If I look at that angle, does anybody remember what type of angle we call it that is being made with the vertex being at the center of the circle and the radii being the sides of the angle? If the angle starts at the center of the circle, it's called a central angle, right? You guys remember saying that the central angle, which we're seeing right here, is 120.9837, is the same as the arc that it intercepts or that it creates out here? And you're seeing that blue arc, remember that blue arc right there is that number. Is that number right there the same as that number right there? Okay? So as this point moves backwards, okay, so let me put another angle. I know it's getting messy here. We'll put another angle in here. Let's make that angle, we'll make it dotted lines so we can differentiate. All right, so basically what I'm showing you here is that if I've got point E and it's on the center of the circle, then we get that 120, we get that angle measurement to be the same as that arc, right? But as I pull that angle back out and away, what is happening to that 120 now? It's shrinking, right? Getting smaller and smaller. And once I pull it away to where it becomes point B, it has shrunk to exactly 1/2 of its original measurement. Is that okay with everybody? So a central angle, okay, that intercepts the same arc that an inscribed angle does is always a 1-to-2 relationship as the inscribed angle. Okay, so that central angle and that inscribed angle are still 1-to-2 because they're both predicated off of the blue arc. So they'll ask you questions like that. They'll clutter the picture. Instead of just giving you one simple inscribed angle, they'll clutter things like this, and you have to play that, kind of that puzzle or riddle aspect of geometry that we've seen all year to figure out the values that we need. Okay? So if I see an inscribed angle, I like, for whatever reason, if they give me an inscribed angle, I like to highlight that inscribed angle. And then I highlight the arc that goes with it. So how big should that yellow arc be if my inscribed angle is 50? If that angle is 50, how big should this yellow arc be? Should be 100, right? It should be twice as big as that angle. So as you move out from an inscribed angle to the arc, you get bigger, okay? So you need double that. So I get 100. So if I know P to Q, that arc is 40, then Y has got to be 60. Good. Okay. Now if I look at the other inscribed angle they give me, which is X, I don't know that measurement, but I do know its intercepted arc, right? So if its arc is 40, working back this way, the angle needs to be 20. Is that okay with everybody? Okay, so you just got to figure out which way do I need to go. Do I need to double something, or do I need to cut it in half? Okay. So that relationship creates this corollary, which hopefully this makes sense. Let's say that this arc right here would you guys agree that arc is the arc for it is the intercepted arc for angle 1. You agree with that? So let's say that angle 1, let's do it this way. Let's say that green arc is 60 degrees. What would angle 1 be? So work back, it's got to be 30, right? Okay. Now let's do this. If I cover up angle 1 and I look at angle 2, is that an inscribed angle still intercepting the same arc of 60 degrees? So what does angle 2 have to be? 30 degrees. So what we find out is if we have two inscribed angles, the red one and the blue one, and they intercept the same angle, the angle 1 and angle 2 should be congruent angles. Because of that 1/2 relationship, I'm never going to be able to take 60 and divide it by a half and get something other than 30 back, right? Every time. Okay? So that's a corollary. We can view it as a theorem, but it's not, like the proof of that is what we just did. It's not very extensive proof. Okay? How big is a semi, in terms of degrees, how big is a semicircle? 180. So what I'm going to try to do here is develop a diameter for this circle. And I'll clean some other stuff up. Let's get rid of, hide that, hide, nope. All right. So when I find the intersection here of the circle and that line, because that line goes through the center, I know it's a diameter. So that dotted line is a diameter. Everybody okay with that? If I take and try to make this circle there we go. If I take and make this inscribed angle, okay, intercept a semicircle, meaning that this point there goes to the end point of that diameter, and this one goes to the end point of that diameter, or that end of the diameter, how big is our inscribed angle now? Our intercepted arc, which is this blue arc here, is 180, but the inscribed angle is half of that, so it's 90, right? Okay? No matter where this diameter goes, so if the diameter is there, and I make C go to H, and D go down to their G. Now, I'm not getting exactly on G and H, but pretty close to 90 degrees, right? Okay? So what we end up learning here is that an inscribed angle in a semicircle, is always going to be a right angle, because you're always, in a semicircle, you always have 180 degrees as being the arc. Okay, so we got minor arcs which are less than 180 or less than 90. No, let me rephrase that. Minor arcs less than 180, major arcs greater than 180. So then 180 is that kind of that threshold. So that we give that a new name. We call that semicircle. Okay, so if you inscribe, the way we phrase it is we inscribe an angle in a semicircle, then it is a right angle. So if it produces a right angle, we now have a right triangle, correct? And we know a lot about right triangles that might allow us to work with the circle and learn other things about the circle. Here's one of those. It says if a quadrilateral is inscribed in a circle, then its opposite angles are supplementary. Okay? Quadrilaterals in general do not have opposite angles that are supplementary. Okay? So let's say that I give you and I'll go back to that so you can write down, I'm sorry. What angle would be opposite angle A? C. Okay? If I ask this thing to find these measurements of this quadrilateral, so find those angles. Those are the angles for A, B, C, and D. Are opposite angles supplementary in that quadrilateral? Does 97 plus 112, does that equal 180? They're not, right? Okay. When we do this, though, let me create a circle here. And let's put so I'll put 4 points on this circle. It doesn't matter, I'll just try to make it kind of drastic so it doesn't look like a square or a rectangle. So that's quadrilateral, correct? If I ask to find the angles of that quadrilateral, if you take 90 point, so the opposite angle here would be that one, okay? If I take those two numbers, 90.6683 and 89.3317, if I add those together, I'm going to get 180. If I add basically 142 here and 38 there, is it 142 plus 38 add up to 180? Okay, so if your quadrilateral is, the way we write this, the quadrilateral is inscribed in the circle, okay, then opposite angles will always add up to 180. And the reason for that, we're going to draw a picture for this. Look at what happens is if I look at angle 1 is going to intercept that arc right there. Would you guys agree with that? So angle 1, I'm just going to write it over here, measure of angle 1 would be 1/2 of the red, correct? Okay. If I look at angle 3, which would be opposite that, angle 3 would be 1/2 the blue, right? So measure of angle 3 equals 1/2 blue. Okay, if I went measure of angle 1 plus measure of angle 3, is that 1/2 of red plus 1/2 of blue? Okay, so now what does that right-hand side of that equation, what do both terms have in common? On this side right here, they have the 1/2, right? So measure of angle 1 plus measure of angle 3 equals 1/2. I'll factor that 1/2 out, and I get red plus blue, right? In the parentheses. Well, what's red? Look at my picture. What is red plus blue? That's the whole circle, right? How many degrees is the whole circle? 360. So if I put 360 in here, times it by 1/2, what do you always get? 180. So measure of angle 1 plus 3, which were opposite angles, will always equal 180. We do the same thing with 4 and 2. Does that kind of make sense? Okay. So that's the reason why a quadrilateral inscribed in a circle has always opposite angles that are supplementary. Is that okay with everybody? Let's take. I don't want to do this stuff. There's some other stuff that goes on throughout here with other angle measurements and scribed angles that I don't want to talk about right now. Let's take what we've learned so far today, see how well we can use that on our assignment, and we'll go from there tomorrow. Does that make sense? Okay. My plan for tomorrow, lost it. Section I don't have the section written down. Section 12.5. Okay, so we'll do some algebra stuff tomorrow in section 12.5. We've already seen a lot of this, though, from the Pythagorean theorem in the distance formula. But we'll start with this equation of a circle tomorrow.